Okay, this is the video that goes with the latest lab. So this is for Astronomy 400 Lab's supernova explosions, and it gives you some background on the supernova. If you took the lecture course about the stars and the galaxies, you would have gone over supernovas. If you took the one about the solar system, you probably didn't. But in a nutshell, the sun will fuse hydrogen into helium, and helium into carbon, and then carbon will be the end for the sun. It doesn't have enough mass to produce the type of temperatures needed at the core in order to go beyond carbon. But bigger stars, they will keep fusing and fusing and fusing. So what we want to do is basically the sun will fuse hydrogen into helium. So what we'll do is we'll do it just like the sun does. So now you got the link right here. Okay, but another way to do it is you come over here, you go to Google, you enter PHET into Google, you should get PHET, free online physics, whatever. Click on physics, and then come down here to build an atom. Build an atom. Click on that. So we want to build the atom. So I click on build atom. Okay, now what determines where the element is in the periodic table is the number of protons in the nucleus. So I put 1 on there, I got hydrogen, okay? So there's hydrogen. I'm not going to mess with the electrons. Electrons aren't critical here. I'm just going to mess with the protons and the neutrons. So I made hydrogen, okay? Now, that is the hydrogen atom. Make sure down here you click on stable, unstable. So that's a stable hydrogen. We can add a nucleus there, it's still stable. Neutron, now it's unstable. See, when it flops around like that, that's an unstable nucleus. So we get rid of it, put it back down here. Okay, now, so we did that, we built our atom. So we built our simple atom. So we want to make sure stable, unstable is marked. Build a hydrogen atom simply by placing a proton in the nucleus of the atom, just like we did. If the nucleus vibrates, the nucleus is unstable. So anyway, we just put a proton there. It's not vibrating around, is it? It's pretty stable. Even if I take that out, there's our simple hydrogen. We put a neutron in there. It's called deuteron, and then that. If you ever heard of heavy water, one of the hydrogens in heavy water, remember water is H2O. Well, one of the hydrogens has an extra nucleus, neutron in it, so that's why it becomes called heavy water. Okay, so then what we want to do is do what the sun does. It's going to take 4 of those protons. 1, 2, 3, 4. Big explosion happens. A bunch of complicated stuff. I'm leaving out a lot of different stuff that goes on in here. But the end result is a helium atom that has 2 protons and 2 neutrons. So let's go ahead and go back to build an atom. We got another proton. Okay, now we've got unstable helium. Okay, well, to make it. So what we do is we add another. The number of protons is what makes what it is. All I had to do is add a proton and it jumped up to helium. But the number of neutrons just changes what isotope it is. So actually, with just 1 neutron, it was stable. And with 2, it's stable. If we put a third in there, it becomes unstable. So get one of those out of there. Unstable means it's going to decay. It means it's going to break up. Some of them break up more rapidly than others. Okay, so now we've got a stable helium. Okay, so that's what happens here, and then in the end, 2 of the protons they emit a neutrino, and then other things happen. They positron. They lose a positron, a neutrino, and they become a neutral. Okay, and so the proton and the neutrons, and then we got the helium over here. Okay, we got a helium nucleus. It's the helium nucleus with 2 protons and 2. Oh, whoops. I've already uploaded this one. I have to upload it again, I guess. 2 neutrons. Stable. The answer, well, we kind of saw that. All right. Now, the next thing that would happen is that we would smash 2 heliums together. Okay, because remember, the sun in 5 billion years is going to run out of hydrogen at the core. It's going to have a lot of helium. Helium is harder to get to fuse because of the more protons in the nucleus. And of course, protons repel each other unless you get them close enough like they are in the nucleus in this thing called the strong force, which is attractive. glues them together. But if they're not right next to each other, it's the repulsive electromagnetic force that keeps them apart. So you got to overcome that electromagnetic force. Okay, so now we want to do is we want to add. So just keep adding here. So we're going to add another helium. We got a helium here. How do we add another helium? We put in 2 protons and 2 neutrons. Proton, unstable. We got lithium now. Put on another proton. Now we've got beryllium. Okay, Be beryllium. Now it's unstable, so you're going to keep adding. Oops, it's still unstable. Oh, you had to add a 5th one to get it to be stable. Okay, the problem is that's not the one that's going to come about when you put 2 heliums together. So we get an unstable beryllium. Okay, so if we try to find another stable beryllium, we can go back to this. Let's make it 3. Only 3. That's unstable. Unstable. We'll break apart in no time. So we go back to adding. So atom. So you basically can mess around. Atom. You see when it's stable, add more, and oops, it's unstable again. Unstable. Okay, we'll get rid of those. Okay, so basically that's what you want to do there. Find out what stable beryllium is, but that's not going to be the one that's at the core of the sun, because it's 2 helium smashing together. That gives you this beryllium for an incredibly small fraction of a second. Incredibly small fraction of a second. Okay, so you can try other ones. So now we have a lot of helium flying around. If the temperature is great enough, what happens is we can smash, in other words, if you smash a neutron in there, we get stable beryllium. But beryllium is not one of the more abundant elements in our universe. So that's not seemingly what happens very often. It happens because we do have beryllium, it exists. But something else exists at an even greater abundance. Let's see what that would be. Let's say that we get it hot enough to the point where we could smash another helium in there. So how do we smash another helium in there? We just add 2 protons and 2 neutrons. So I'm adding a proton, we got boron. Adding a proton, we got carbon, but it's unstable carbon. Adding a neutron. Now we got 1, 2, 3, 4, 5, 6 neutrons, 1, 2, 3, 4, 5, 6 protons. We got stable carbon, and carbon is very abundant. This would be called carbon 12. All right, so go down, we add carbon, blah, 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 and then you can keep adding more and more protons to this. We add that guy, we get unstable nitrogen. I want to make it stable, so I do that. It's now stable. Add another one, we get unstable oxygen. Add another one, we got stable oxygen. Add another one, we got fluorine. Add another one, we got unstable. We got to add a couple to get stable fluorine. Add another one, we get neon, stable neon. Neon stays stable for a lot. Oh, there's unstable. I can add these guys. Now here's the whole point. Now we get unstable neon, but we've run out of. Oops, I don't want a proton. I want a neutron. So now we're over to here. Now we've run out of protons, so we can't make the rest of these. But these guys still exist. The sun cuts off right here at carbon. Okay, this is where the sun cuts off at carbon. The sun's going to become a big ball of carbon because it can't go any further. It can't start fusing when all it's got is carbon. It doesn't get hot enough. The gravitational force isn't great enough. The gravitation isn't great enough in order to cause more elements to be nuclear synthesized. Okay, so as a result, these don't come from a star like the sun. But bigger stars will keep going and going and going until they get to right here, Fe, that's iron. Iron is the most stable nucleus there is. That's the end point of fusion. You can't get any more energy out of this. The way they were getting energy before is that if you take 4 hydrogens and get 1 helium, the 4 hydrogens total mass was greater than the mass of the helium. And you had Einstein's E equals mc squared. It's all in the lab. It's written up in here. It's back here someplace. It was back here someplace. And now I cannot find it. I'm trying to go through this too fast, maybe. But anyway, the mass, the extra mass, oh, there it is. The extra mass is what gets turned into energy. That's just the speed of light squared, 3 times 10 to the 8th meters per second. That's a constant. So the mass gets turned into energy. So the mass that the hydrogens have that didn't end up in the helium, that gets turned into energy through a gamma ray. Okay, so what's happening in here is that one of the positrons that comes out of the proton to make it lose its positive charge and become a neutron, that runs into an electron. They annihilate each other and they produce a gamma ray. And that gamma ray is the very beginning of a whole train that goes from the core of the star up to the surface. Okay, and it turns into other types of radiation as it does this. Okay, so then we messed around with this, and then you can add and add and add. But where do all these other ones come from? Look, here's the periodic table, and then this is iron right here. Well, the sun stops at carbon. Bigger stars, 8 times the mass of the sun. I mean, huge, really huge compared to the sun. Once you get to iron, you can't get any more energy through fusion. You got to do the fission. You got to split the atom, not fuse the atom. So how do we get all these? Well, desperate stars. At the very, very last moments, the stars just keep fusing horrendously, ferociously, to try to come up with some other source of energy, but it's too late. But these elements exist. Cu is copper, Zn is zinc, As is arsenic. Okay, you heard of people with arsenic poisoning. Si is silicon. Well, silicon is before iron, but Silicon Valley. All right. So, but then all these other ones come about because the star Sn is tin, right? And so silver, Ag is silver, Au is gold, mercury, lead. Okay, these are a lot of very famous elements that come along only after the stars run out of energy. Okay, so what happens there is that the star just keeps doing it, and it creates a iron core. And the iron core, you can't get any more energy out of it. Things heat up. You do all this incredible stuff. Basically, it just to cut through. There's like things called neutronization and photosynthesis or photodisintegration. All this other stuff takes place. But in the end, you got this iron core. Gravity shrinks it down, but overshoots. Okay, you get this thing called electron degeneracy pressure. I think it ends up being neutron degeneracy pressure at this point. It's neutron degeneracy pressure. You squeeze the neutrons too close together. So you got a big ball of neutrons at this point because things happen. And that ball explodes. It rebounds with a vengeance and spews everything out into space. The iron, the gold, the silver, the copper, the cobalt, the carbon, the beryllium, the helium, everything gets spewed out. The tin, the lead, the whatever. It gets spewed out in space, makes a big cloud. The cloud condenses and it forms a star. That's how our sun formed. That's how our solar system formed. Once a long time ago, before our sun even existed, before our solar system even existed, way more than 5 billion years ago, a star blew up and put all these elements out into space, and they came together and they created the Earth. Okay, so now what we want to do after you go through all that is you want to go to stellarium. Let's look at it on here. So we go through all that, and you can read all this. Okay, there's what we call the Crab Nebula. Okay, so why don't we go back now? The progenitor, that's the star that blew up and went supernova. So what star blew up? It doesn't exist anymore. Okay, it hasn't existed for a long, long time. So what we do is this: in the Middle East and Asia, and other places on the surface of the Earth, we found historical writings that write about this big bright spot in the sky that may have been as bright as Venus at its brightest. That's how bright that thing was. It just showed up out of nowhere. It's not there. It's not there. The sky's the same. Sky's the same. Boom! There's this big bright thing that wasn't there yesterday. What the heck happened there? Well, this progenitor, this star, blew up. Okay, and this is what's left over of it. So then, what astronomers did was they went back and they said, okay, these gases are moving out at a certain speed. Okay, we can extrapolate back to when all this was at one point. So how long ago, if the gas is this far out and it's moving at this velocity, okay, how long ago would it all have been at one point right here? And it would have been the year 1054, right around when the writings reported this bright object appearing in the sky. So we've got the historical writings, we've got the current technology giving us new data to look at this, and it all comes back to about 1054. Okay, so let's go to stellarium. You open your stellarium. I got it on Jupiter now, but I want to go to the Crab Nebula. So you get this, and you go CRAB for crab. Okay, and then you see a nebula there, but you can't click on that. You got to type it out. You can on the one that I think goes with the browser, but that one looks like it's not as powerful as this is. So I go Crab Nebula. Okay, well, run through space. There's the Crab Nebula. Okay, you can't really see it from Earth with the naked eye. Okay, it's way out there someplace. You put the Earth on. See, remember, you got to turn the Earth. See, right now it'd be there, but then if we turn the sky on, we couldn't see it because that's kind of where the sun is. Okay, so there's the without the Earth, and then here's without the atmosphere, and there's the sun. We come into the Crab Nebula. So now, set this. So set, I want to get this. So set it to January 1st, 1054. So I come along here and I go make this one, oops, went too far. Make this 1054. Look at that. There's a star there. You don't have the Crab Nebula there anymore. So this is 1054. Okay, almost 1,000 years ago, right? Well, no, way over 1,000 years ago. Right? Yeah. No. 20. No, not. In 2054, it'll be 1,000 years ago. So some of you will still be around then. Hopefully, all of you will still be around then. That's only 34 years away. Okay, so let me go month by month. So there's February of 1054, nothing. March, April, May, June, July, August. Whoa! So something happened in July of 1054. It blew up in that month. So now what you want to do is start messing with the dates. So just keep clicking up, and then you'll get the date. I was going to ask you to get the time too, but I'm just going to ask you to get the date. So then all you do is you go through, you click through, and then see what year, what month, what day was the approximate date for Supernova 1054. Okay, again, I haven't even started making your, this will not be on your exam. Okay, you have your exam Wednesday night, and so I made this due Thursday. I can make it due Friday. I can go back and make it due Friday instead. But your exam will be Wednesday night. It'll be over the other 4 labs that we did. So you can see Supernova. This one's up now, but I'm gonna, you know what? Just remember that correction I made. I don't want to go through and oh no, I better. Okay, I'll re-put it up. All right, so these 4 here: the planets 1, the planets 2, orbits of the planets, and the moon. Now remember that because normally the rule would be you can't use the labs on your exams, right? You got to just kind of remember stuff. Well, that means if I make that rule, the honest students won't use their labs, and the less than honest students will say, oh, he can't see what I'm doing, because I'm not looking in your window while you're taking this. I have no idea what you're doing. So the rule is everybody can use their labs, the 4 labs here. But when I make this exam, and I was going to start it today, but now that I'm not giving it tonight, I was going to start it yesterday, but now that I'm not giving it tonight, I didn't start it yet. I got to start at Sac State next week. Ooh. All right, so you can use the labs. Remember, when I make this exam up, I'm going to have in the back of my mind that you have access to the labs. Okay, so keep that in mind. So you want to make sure you know where stuff is on the labs, because you want to be able to get to them, I guess, pretty quickly, because you may not, it's not going to be an exam where I just assume you just kind of know this stuff because it's so simple, you better know it. It's going to be one where, oh, they might know it or might not, but they know where it is in their lab if they don't know it, okay? And that'll be Wednesday night, a week from last night. All right, let me say good night for now and then upload this.